Hello all. Now we will see the next topic from the unit number 6, that is fractals. Before fractals we have seen the curves and the type of curve generation. After that we have seen the different curves and how the equations are used to draw that particular curve. Now we are going to see fractals. If we have a curves, we have the equations of curve, we can draw the curve easily. Then why we are moving towards the fractal? So the thing is that the objects which are having the smooth surfaces and the regular shapes, that can be shown by using equation. But the objects that are very natural like mountains, trees, ocean, waves, etc., etc., these objects cannot be having a regular shape. They are in irregular shapes, and such shapes cannot be represented by using only that curve concept. So we are going to see this fractal concept. So the question on these fractals can be like, discuss the topological and the fractal dimensions, and or it may be like write a short note on the fractals, or write down the fractals with the suitable example. This can be a questions, and this is also very important part of this unit. Now we'll see exactly what is the fractal and concept of fractals. So it is very difficult to draw the irregular shapes using such a normal equation we have seen in curves. So there are many methods of modeling this natural object, and one of them is a nothing but fractals. So to show such a irregular shapes, there are many methods to model that shape. From that, the fractals is a one concept. So we have to describe this natural object by using fractal, where we are not going to be use an equation. Rather than equations, we are going to use the procedures. Means whatever the procedure we are defining, we are following that procedure repeatedly to find out the fractals. So procedurally defined object have a characteristic, so something different from the objects which are defined with the equation. So they have something different characteristic. So the one of the basic characteristic between this different characteristic is the basic properties that categorize the fractal. That category or characteristic is self similarity. This is the very important characteristics of this irregular shape, that is self similarity. What is this self similarity? It says that this property is nothing but if an object can take a different forms depending on the choice of their representation, such a property is called as a self similarity. Means what? If we zoom out the piece of that fractal part or a fractal, then we will see after some same structure is repeated over and over again and again, following the same pattern again and again, that is called as a fractal. Means what? It is based on the self similarity, where the same structure is repeated over and over, that is called as a self similarity. So again we have the different types of this self similarity. That types are nothing but there are three types: exact self similarity, quasi self similarity, and the statistical self similarity. So these are the three different type. The first is exact self similarity. It means that in this type the fractal look like a same or identical at any scale, at any different scale it look like a same. That is called as a self similarity. It is very strong form of the self similarity. Means every part is repeated again and again with the different scale. It look like a same at all the different scale. That is called as a exact self similarity. The next type is quasi self similarity. In that the fractal appears approximately but not exactly identical or a same at a different scale. That is called as a quasi self similarity. Means it is a nearly approximately same but not exactly same. Then next is a statistical self similarity. In this pattern there is a random fractal are drawn. Means it is very weakest type of self similarity, and in that type the fractal has a mathematical parameters maintained throughout the scale. So there are not a fixed pattern, the mathematical parameters are maintained to that different scales. So this is what the three types of the self similarity, which is very important characteristics of the object which is defined under this procedure part. So we'll see one example how the object will look like when we are seeing or observing that object from the different distances. So from a certain distance, if we see a coastal line, this is what the coastline, if we are seeing from that certain distance, then it look like a simple line or a quite smooth line, we can say. But if we zoom that, or if we go near to that line, then it will look like somewhat more rough than the previous one. So if we take a closer view, then we can see that the whole line is a very rough and jaggy. So in that case, there is no limit to how many times we can zoom that line, and these are the same line, but if we are viewing that line from the different views, then it may change. And whenever we are seeing that line very closer, then we can see here that line is something jagged and very rough one. So this was the concept of the lines which are different from the different view. So fractals are nothing but the complex pictures which are generated by a computer from a single formula. Means we are going to apply the same concept, same procedure, same formula repeatedly again and again on a fractals. So they are created using repetitive steps. This means one formula is repeated again and again with a slight variation in the parameter or values. So every next iterative step is depends on the result of your previous step. So this is what the concept to generate the fractals. Means what we are going to use here, nothing but the repetition of a same formulas, that is called nothing but factors. So there are many applications of a factor, like in the medical research science, we can use that for analyzing the bacteria cultures, then study of the genes, then humans, anatomy, etc., etc. That concept is used over here. Then in chemical research also, for the simulation of the chemical reactions, then atomic culture, this etc. fields, we can use the fractal concept over there. In the space research also, for the study of galaxies, then the simulation of stars and their behaviors, the concept of fractals is used. Other than this, there are we can use them to represent the fractal art, then video games, image processing, etc., etc. So these are nothing but the applications of fractals which are used to show the irregular shapes, or we can say the natural objects. Then after that, this is what the its characteristic, that is self similarity. These are nothing but the different views, and this is what the application. Now how we are going to find out that dimensions of the fractal? So for that, we are having the topological dimensions over here, and what the topological dimension says, now we'll see. You have to imagine that suppose there are one object and you are breaking that object into the line segment. You have one of the object, and if you are making the object as a line segment, then you can say that it is having the dimension of a 1. That's why I am showing the dt is having the value 1. If you are breaking that object into the plane, if you are making the plane of that object, then plane is having the two values, that is x and y. So dimensions of that plane will be 2. So dt is representing the 2. dt is nothing but topological dimension. If the object is a 3D object, all of you know we are showing that object by using the 3D coordinate system. So in that, the dimension dt will be 3. So these are nothing but the topological dimension, where dt is shown as a topological dimensions. Now you can assume or imagine that we have one thread, say the thread of 5 centimeter. Okay, we are having one thread of 5 centimeter. If we want to cut into the 5 equal parts, then each sub thread having the length of 1 centimeter. It means we have to scale the thread or a line by 1 by 5. Means I want to break one thread into 5 parts. So how I am going to do that? By making 1 by 5 equal parts. If we want to build again the original line from this different parts, or we can say the different object that we have created, and if you want to make the original object from that 5 different parts, then obviously how many parts we require to draw a original line? Same 5 parts will require to draw the original object, right? So here we can see that this line is having the 5 centimeter of its length, and if we break that line into the 5 equal parts, then the value of n will be 5. I am making that line, the number of pieces of that line is equal to 5. So each part is having the length of 1 by 5, means 1 centimeter. Each line is having the length of 1 centimeter, because the line of single segment is equal to the total length of the line divided by the number of parts, that is L by N. 5 by 5 is equal to 1 centimeter. So what is the scaling factor is here? Scaling factor means by which value we have to scale the line? 1 by 5. That is nothing but the scaling factor. So scaling factor is 1 by S, is nothing but 1 by 5, means S is having the value is equal to 5. How we are going to represent? The scaling factor is shown as a 1 by S. 1 by S is equal to 1 by 5, and therefore the value of S is nothing but 5. So N is showing the number of scale object, that is 5. We have scaled it by 5, 1 by 5. So S is showing the scaling factor, that is 5. So what is the value of N here? N is nothing but S raised to 1. That is what the value of N. N is nothing but number of scale object. So N is what? S raised to 1. N is having the value 5. S is having the value 5. 5 raised to 1 is equal to N. 5 is equal to 5. This is what about the topological dimension is equal to 1. If I am saying that my topological dimension is equal to 2, means I am having the example of a plane where we are drawing the we have drawn here the square, right? So now if we are considering that square, and if you want to scale it by 1 by 2, 1 by 2 means half of that its original size, then how many small square will get generated? If I want to make this square as a 1 by 2, then how many small square will be generated? So you can see here the 4 small square can be generated if I am making the size of this original square as a 1 by 2. So the scaling factor is 1 by 2. If you want the original object, this square, then how many squares we are required? Small square we are required. Then we require the 4 small square to get the original object. So here again you can say the scaling factor is 1 by S is equal to 1 by 2. Therefore S is equal to 2. And how many objects are created? 4. N is equal to 4. So how you can form the N? By using S. So you can say here N is equal to S square. Means N is 4, S is 2. So 2 square is 4. Then you are getting the N is equal to 4. So this is what the topological dimension having a value 2. In that case the concept will be N is equal to S square. Now if we are considering the cube, whenever we are considering the cube, then it will and if you want to scale that cube by half, if we want to scale that cube by half, then we need n number of scale object, right? So how many objects will require scale objects? So here it will divide that into the 8 parts. It will divide that into the 8 scale object. And if we want to form the original object, so what we have to do? We need the 8 scale object to form the original object. So these are nothing but the this is shown in this cube format. So here we are making the scaling of half. That means the scaling factor is equal to 1 by S is equal to 1 by 2. Therefore the value of S is what? 2 here. And in how many parts it is going to be divided? That is nothing but the 8 parts. So N is having the 8. So how we can match that N and S? So we can say that N is equal to S cube. Means N is equal to 2 raised to 3, that is 8. So N is what? 8. So in that way we can find that how many small parts is going to be formed for that object with the given scaling factor, that we have to found here. So we observe that from this given equations, that is N is equal to S raised to 1, N is equal to S raised to 2, or N is equal to S raised to 3. By seeing this equation we will come to know that there is some relation, that is exponent goes on increasing. We can see that the exponent is going to be increase over here. So there is some relation, and we can generalize that relation by using this equation, that is nothing but N is equal to S raised to df. N is equal to S raised to df. What is this df? This df is showing the dimensions, and that dimensions are called as a fractal dimension. So n is this df is showing that dimension, that is 1, 2 or 3. These dimensions are shown by this df value, and that df is called as a fractal dimension. So how this df should be calculated? So df is calculated, that dimensional df is calculated as a log of n divided by log of s. So by calculating the log of n and divided by log of s, you can find the value of df, and by finding the value of df, you can directly find the value of n. So this is what the fractal dimension df, which we are going to use for the next fractal generations. So this is what the concept of fractal. We have different methods to create a fractal, and in that we are going to use this df concept, that is a fractal dimension. So here we have seen what is the concept of fractals, which is very important for drawing the objects which are irregular in a shape, that is nothing but the natural object. Thank you.